recording.
Okay, very good. Thank you. So first of all, thank you very much to Sonia and to Joey for this wonderful opportunity. I will tell you about a long joint project with Sue Tolman. It's been going on for many years. A big part of it has been published. There's a piece that has not yet been published. When I get there, I'll tell you which piece is of which status. And this is about complexity one, Hamiltonian torus actions. And let me begin by sort of telling you, or reminding you about, in general, about Hamiltonian torus actions. So we have a symplectic manifold, and we have a torus acting on it. By definition, a torus is a Lie group isomorphic to just a product of circle groups. And we have a momentum map. What does that mean? Well, if you have any element of the Lie algebra of the torus, it generates a one-parameter subgroup of the torus, which then acts on the manifold. That's a flow on the manifold. So that flow has a vector field that generates it. That's psi subscript m. On the other hand, if you take your momentum map, that's a function to the dual of the Lie algebra of the torus, and you evaluate it at each and every point on the Lie algebra element psi, what you get is a real valued function on the manifold. So these are the coordinates of the momentum map. And we would like the coordinates of the momentum map to generate the corresponding flows using Hamilton's equations. So the d, the zero derivative of this real valued function, that's a one form, should be the same as contracting the two form with the corresponding vector field. One of the consequences of this Hamilton equation, not true for non-abelian groups, but is true for tori, is this momentum map is automatically invariant under the torus action. So we get a so-called orbital momentum map, a map from the geometric quotient to the dual of the Lie algebra. This is not supposed to be obvious, but there's a little proof there. So we would like to classify these guys, and we will need to make some strict assumptions to be able to do that. But in general, when you talk about classification, what does the momentum map gives you? It somehow allows you to spread out the manifold and work with sort of little pieces of the manifold. If this is the manifold, and this is my momentum map, the target space is T star, I could study separately. Here's a vector in T star, alpha. I could study separately preimages of little neighborhoods inside T star. And this is somehow an intermediate object between the global and the local pictures. And I'm going to be, again, my goal is to sort of reach some statement of classification, but the proof goes through understanding these semi-local pieces and how they assemble together. So the idea for the proof of the classification, which I'm hoping to state toward the end, at the end of the talk, is, understand the pieces locally. And that means work with neighborhoods of orbits in the original manifold. And then semi-locally means understand preimages of little neighborhoods of T star. And then globally means you need to study how these pieces fit together. So the proof actually goes through a sheaf theoretic machinery to do that. And I'm not going to talk about that part of the proof. And to be able to do that, you need some assumption. We assume that the momentum map is proper. In particular, this works when the manifold is compact. Now, let's start with the local picture. Just tell you or remind you of the building blocks for Hamiltonian torus action. Again, at this point, any dimension. And we call these building blocks Hamiltonian T models. You can actually, write down very explicitly what they are. So what is a Hamiltonian T model? It's a very explicit example of a symplectic manifold together with a Hamiltonian torus action. So if I start with my torus, I will pick a closed subgroup. Maybe it's a torus or maybe it's disconnected. That group will act on C to the L, just R to the 2L, by rotations of the coordinates through a subgroup of the standard S1 to the L action. And it will have a momentum map, a quadratic momentum map, taking values in the dual of the Lie algebra of the group H. This map can be explicitly written as the summation. This is a sort of a positive or non-negative linear combination of elements in H star. These elements are just the, if you follow the definition, these elements are just the weights for the H action on CL. And as soon as you have this little linear piece, you can cook from it the Hamiltonian T model. You start with the product of T cross CL cross. Now, what is this H naught? This is a subspace of the dual of the Lie algebra of the torus, consisting of just the annihilator of the Lie algebra of the subgroup H. So the fructor H will be the Lie algebra of the subgroup H. Fructor H, not, superscript 0, that's its annihilator. Now, in this ambient space, T, the torus T cross the dual of the Lie algebra, this is just a cotangent model for the torus. This comes with a standard symplectic structure. So does C to the L, identified with R2L. So here we have a standard symplectic structure on the one hand. On the other hand, this triple product descends to our model. Our model will be the quotient of this triple product by the action of the group H, which is the given action on C to the L, and just write multiplication on the T factor, maybe through inverses of elements of H. And this standard symplectic structure upstairs descends to symplectic structure downstairs. In fact, this is just a special case of symplectic reduction. So we have a Hamiltonian torus action on Y. The torus acts by left multiplication, and the momentum map can be written very, very explicitly. You need a little choice for that, but it's the same formula. So an element in the model is represented by triple TZ nu, where T is in the torus, Z in the C to the L, and nu is the annihilator of the Lie algebra of H. And the momentum map takes it to some constant, I don't care what it is, plus we apply the quadratic momentum map to Z, and this gives us something in the dual of the Lie algebra of H. And then we just add nu itself, and this is inside the annihilator, and we're secretly identifying T star with H star cross H naught. And if you stare at this formula long enough, really the interesting part of it is just coming from, the linear piece here. What is happening with that linear piece? You're taking norm squared of each coordinate. That gets you to the positive orthant. And then you have you sort of drop by a linear projection that takes the standard basis elements to the weights, to the eta j's. So this map has some very nice properties. This map, as well as the eventual map that we built from it, its image is a convex polyhedral cone. Its level sets are connected. And topologically, this map is an open map as a map to its image. So if you start with an open set, you will get a set. Its image will be open in the relative topology of the entire image. The local normal form tells us that these guys are the building blocks for arbitrary Hamiltonian torus actions. So this is what I'm writing here is a special case of a more general local normal form due to Gilliman, Sturberg, and Marlet. It says that this version says that for every Hamiltonian T manifold and point in it, there exists a corresponding Hamiltonian T model. And again, if you stare at this long enough, that T model will be unique up to permutations of the coordinates in C to the L. So here's the T model. Hold on. Such that a neighborhood of X in the manifold is isomorphic to a neighborhood of the base point in the model through an isomorphism that takes x to the base point. And isomorphism here means equivariant simplex isomorphism that preserves that intertwines the momentum maps. Intertwining the momentum maps is a very mild condition here. The momentum map is determined by the action up to translation. Do we have questions so far? I think everyone is muted, so I'm hearing a big silence.
I mean, I suggest that if somebody has a quick question, they should just ask politely. And if there's some major stuff or something which may take longer, we just do it at the end. I mean.
Yeah, sure. So actually feel free to unmute yourself and sort of interrupt me. Okay. So we have some very nice topological. So what we have here from this local normal form is some information of what the momentum is. Yeah, someone had a question. No? Okay, sorry. So what we have here, we get some sort of, we can sort of get exactly the local picture for everything, symplectic structure, the momentum map, in particular, the topology of the momentum map. And these local behavior of the momentum map can actually be pulled together to conclude some global properties of the original momentum map, which again, if I had an extra 10 minutes, I would give you the beautiful proof. But let me just stick with this statement. So we call this convexity package for Hamiltonian torus actions. Here's the symplectic manifold. I do want to assume that it is connected. We've got the symplectic torus action. It is Hamiltonian. It has a momentum map. And for this convexity package, I do want to assume that the momentum map is proper. And the convexity package gives us three things. First of all, that the image of the momentum map is a convex polyhedral. It's a subset of T star. It's close subset of T star because the momentum map is proper, and it is polyhedral. So locally, these pieces look like pieces of convex polyhedral cones. And the momentum map is open as a map to its image. And the level sets are connected. Moreover, for every convex subset of T star, its preimage is connected. So it's a little bit stronger. So for example, to visualize the openness of the map, here is the manifold, and here is the momentum polytope. And I might have a point here, X, maybe it goes to here, maybe it goes to a corner, for example. And if I want to know, if I'm looking at a little neighborhood of X in the manifold, it will go to a little neighborhood with the relative topology of alpha inside delta. So if I want to know what delta looks like inside alpha, I don't have to search through all the preimages of alpha. I can just search through a little neighborhood of one of them. So let's now introduce the next notion. So the word complexity occurred in the title, and low complexity is absolutely essential to be able to get a sort of global understanding of these guys. Up until now, this works for any complexity whatsoever. So here we go. Again, I would like to assume that I have a connected symplectic manifold with a Hamiltonian torus action. And it turns out that the dimension, if the action is faithful, the dimension of the torus is no more than half the dimension of the manifold. And just to be a little bit pedantic, if the action is not faithful, let me just divide by the kernel of the action. And the complexity measures is how far are we from reaching this maximum dimensional of symmetry. So an action of complexity 0, that's the same thing as a toric action. I did not, yeah. In this situation, I'm not even assuming compact or proper. Can actually have a lot of good stuff with these guys. But you know what? Let me throw in that assumption just to be safe. And we have the reduced, let's say that this is proper, just to be safe. We have the reduced spaces. The reduced space is the subquotient obtained in the level set modulo the torus action. And this inherits a symplectic form from the ambient symplectic manifold. And this guy is, maybe it's not smooth, but it is a stratified symplectic space defined by Shamar and Lerman. You can do Durham cohomology on it. You can have differential form. You can integrate. You can do a lot of things on these guys. And the complexity turns out to be the same thing as the dimensions of these reduced spaces. That's just a little theorem here. If you fix your attention on reduced spaces over interior points on of the momentum polytope. If you go to the boundary of the momentum polytope, the dimension of the reduced space might jump down. This does happen in our situation as well. Then what do we do with this guy? Let me say a few words. Again, any questions to interrupt me? So we'll be focusing our attention on complexity 1. That's like one dimension off from being toric. And many of us are actually very familiar with compact toric symplectic toric manifolds. You know, these are actually determined up to isomorphism by their momentum polytope. Let's say a few words about Dustrom-Attachman. I will need that. That's going to be one of my invariants. You can actually recover it from, almost recover it from the other invariants, but I'll actually want it. So suppose we have a k-dimensional torus acting on a 2n-dimensional symplectic manifold with a momentum map. And in this case, if you count dimensions, complexity is going, let me call it D. So it's going to be n minus k. And Dustrom-Attachman tell us a few things. One of them is near a regular value for the momentum map, you can identify the reduced spaces with each other, and under that identification, you can say explicitly how the cohomology class of the reduced symplectic structures changes. It changes linearly, and the slope is governed by the topology. So here is the slope. This guy's going to be the slope. So here we have a, so the equality is between elements in second cohomology of the reduced space with real coefficients. And alpha minus alpha naught is in T star. So the guy here is going to be a cohomology class with coefficients in the Lie algebra of the torus. So it pairs together. In fact, the cohomology will be inside the integral lattice of the of the torus, and this coefficient is just the first Chern class of the level set viewed as a principal torus bundle or Orbi bundle over the reduced space. So somehow the Dustrom-Attachman measure. Oh, I'm not yet there. I didn't yet explain the measure. But somehow this class sort of tells you how this variation of this of the cohomology class of the symplectic structure on the reduced space tells us the topology, the twistedness of the level set above the reduced space. And then the Dustrom-Attachman measure by definition, is a push forward of Liouville measure by the momentum map. And we can write it as Lebesgue measure times a function. And that density function, we can express it as some normalization factor times this. Basically, it's the symplectic volume of the reduced space. Over the interior of the momentum corridor. And in fact, it sounds kind of like a fancy thing, but in fact, up to constant, the Dustrup-Takman measure is determined by the topology. So what I mean topology, I don't just mean topology, I mean topology together with the torus action and together with the momentum map. But I don't need here to keep track of the symplectic form. It's up to constant, this is it. So another thing that we see from this formula, because the omega alpha is linear or affine in alpha, and we're integrating its d power, we can see here that the Dustrup-Takman measure will be locally polynomial of degree d, polynomial in each region of regular values of the momentum map. And we will be focusing on complexity 1, so this is going to be piecewise linear. And the slope will exactly tell us the twistedness of the reduced space as a principal T bundle over the quotient. And from here on, I will be assuming that everything has complexity 1. Okay. So I sort of gave you some of the invariants that will be relevant here. Let me say a little bit more. Let me say a little bit more about the proof here. What is so special about complexity 1? One of the pieces, one of the ingredients in the proof is complexity 1 allows us to let go of the symplectic form, allows us to reduce, using Moser's method, to reduce the symplectic geometry to just the covariant differential topology. So we are assuming complexity 1, and we have two complexity 1 Hamiltonian torus sections where the momentum map is proper and the manifold is connected. So I'm going to have the primes on the second guy and then no primes on the first guy. And the little claim is that these guys are isomorphic if and only if two things happen. First of all, there has to exist a diffeomorphism from M to M prime that is orientation preserving and intertwines the torus actions and intertwines the momentum maps. And this, we call this guy by name. We call this a phi-T diffeomorphism. And this is almost enough to guarantee that the manifolds are isomorphic. Sometimes it's enough, sometimes you need a little bit more. We already said that this information already determines the Dustrup-Takman measure up to constant, and we need to have the same constant. So the second bullet is really just one parameter, one real number. So that's one little piece of a lemma. The idea, well, this is proved using Moser's method. If you have such a capital F, then you take the convex combination of your original symplectic structure and the pullback of omega prime under your diffeomorphism. And then you have a whole one parameter family of two forms. And the complexity 1 assumption allows us to prove that this is not degenerate. So these are actual symplectic forms. they have the same momentum map. This is not hard. And again, with the help of the assumptions, including the fact that this is the same Westermann-Heckmann measure, we conclude that this has the same cohomology class. And then you apply, for those of you that are familiar with Moser method, this is a version of Moser method that keeps track of the torus action of the momentum map. And Moser method will tell us that this whole one parameter family of symplectic forms are all isomorphic to each other. So that's the first of two lemmas, starting with the equivariant symplectic geometry and reducing to the equivariant differential topology. The second of the two lemmas starts with the equivariant differential topology and reduces the story to looking at what happens on the level of the geometric quotient. So let me write down that second lemma. So that's the second important step in the whole story of classification. And this too is using the complexity one assumption. Complexity one is used in a very, very meaningful way. Well, if you have a phi t diffeomorphism, then it induces a map on the geometric quotients. And this map has a property that we call phi diffeomorphism. By definition, phi diffeomorphism means that locally you can lift it. So there's nothing symplectic here, but the phi means we're keeping track of the torus action and of the momentum map, but we're not keeping track of the two form. So now this second of the two lemmas tells us that there exists a phi t diffeomorphism between our complexity one Hamiltonian torus action if and only if the following two things happen. One of them, there exists a phi diffeomorphism between the quotients. And second, when they have the same Westermann-Heckmann measure. Now, previously, for the same Westermann-Heckmann measure, we needed it in order to guarantee that we have the same cohomology class when you pull back. Here we're using, and so we only needed the constant in the Westermann-Heckmann measure. Here we actually need the slopes. The slopes will keep track of M, the twistedness of M as sitting over M mod T. You pretend that M is a bundle over M mod T, and the slope of the Westermann-Heckmann measure will keep track of the twistedness of that bundle. So that's the second of the two lemmas that are playing a crucial role in the proof. So we end up just working with the geometric quotients. Of course, the geometric quotients are not, they're not smooth. They're going to have an open dense set where they're smooth. Like there's an open dense set where that torus action is free, and then you get the smooth quotient, and but there's singularities, and these create a lot of subtleness. And the singularities downstairs, they come from interesting orbit type strata upstairs. So I should say a few words about those. And once again, let me pause to see if there's questions.
Yeah, maybe can I ask a question? So your first lemma, does it hold even in the context where there's singularities? So
everything is in the context of singularities. Everything
okay,
is,
okay.
Yeah, everything. So
because because for the Dusterma, I mean for the measure, you would have to do something a little, because you might have some singular spaces, right? Some singular reduced spaces. So.
Yes, absolutely. But the point is, if you know the torus action, that actually determines, and in this first of the two lemmas, we are keeping track of the torus action and the momentum map. And that already determines the entire Westermann-Heckmann everywhere up to a global constant. So in this situation, the second bullet just means we need to have the same global constant. So it captures very little. So basically, if you have the first of the two bullets, this gives you all the reduced spaces, but except that the symplectic area of reduced space in the first manifold might differ from those in the second manifold, but they will differ by constant. And the second bullet fixes that constant. So this is relevant in this situation that we call tall. If you had a point on the boundary of your momentum polytope whose reduced space was a single point, you don't even need that second bullet. In that situation, the distributional Techman measure is actually determined by the torus action and momentum map. But if all the reduced spaces are two-dimensional, none of them are single points, then you do need that second bullet because you can kind of.
Yeah. Mm-hmm.
Does that make any sense?
Yes.
Yeah. Thank you
Thanks.
for the question.
Thanks.
Thank you for the question. Okay, so let's actually say a few words about the orbit type strata. So this is now for any torus section and smooth torus section on a manifold. And what are the orbit type strata? These are the connected components of the sets of points with the same stabilizer. And you let the stabilizer be, well, any subgroup. So these are the strata. So the manifold is a disjoint union of the orbit type strata. And the set of orbit type strata is a partially ordered set, discrete set. Where the partial ordering is one strata we say is lesser or equal to the other if it is contained in the closure of the other. Now, these closures are geometrically quite nice. So if you take an orbit type stratum and you take its closure, that closure will be a smooth manifold, T invariant smooth symplectic manifold. It will be a connected component of the set of points. So previously, the lower H means points whose stabilizer is equal to H. Upper H means points whose stabilizer is contains H, so points that are fixed by H. So the X bars, these are going to be sort of closed submanifolds. So they themselves are sort of smaller Hamiltonian torus actions sitting inside the big one. So this is smooth, symplectic. And if you just restrict the momentum to it, you get a momentum map for the torus section on these guys. Of course, that torus section is no longer faithful. It acts through T mod H. But these are perfectly good. And this is the reason why in my definition of complexity, I insisted to mod out by the quotient of the kernel of the action, because I do want to look at these lower closures of the strata. And then we can talk about the complexity of this guy. It turns out that these guys are always as no bigger than the complexity of the original guy. So in the cases that we actually care about, let me say this verbally, let me not write down. So actually, let me say something about, so we care about complexity 1. So when we have complexity 1, if you look at the closures of orbit type strata, what can they be? They can have complexity 1, or they can have complexity 0. Complexity 0 means that they're toric. So you have some strata whose closures are toric, and these are sort of sitting, these are sort of smaller strata in a sense. Toric strata are, so again, toric strata are just symplectic toric manifolds sitting inside our big complexity 1 space. Let me say a word, those of you who are familiar with symplectic toric manifolds might know this. Let me, maybe I will write something. Suppose that you have a symplectic toric manifold. Let's call it N. And eventually this will be the closure of one of our orbit type strata. These are pretty, so now you can look at the strata inside these guys. So first of all, when you have a symplectic toric manifold, we have the momentum map. Here is the image of the momentum map. And this here is the orbital momentum map. And in the toric case, this is really cool. The orbital momentum map is in fact a diffeomorphism of manifolds with corners, where on N mod T, the manifold with corner structure is induced from N, it's a quotient, and on the target, on delta N, the manifold with corner structure is induced from the ambient T star, it's a subset structure. But this is in fact a diffeomorphism of manifolds with corner, which is pretty cool. And in the toric case, there's a, you can actually see what the strata are. The orbit, so inside N, its lower strata themselves are all of them are of complexity 0, and the orbit, so all of its strata are themselves toric, and the orbit type strata of M under the momentum map exactly correspond to the strata of the momentum polytope. What are strata of a polytope? These are just the relative interiors of the faces, that's all. So at this point, I need to sort of tell you how these guys are sitting in that. Well, no, so for toric guy, the orbital momentum map just identifies it with a subset of T star. So if that toric guy was sitting inside a bigger ambient complexity 1 Hamiltonian torus manifold, on the level of the quotient, it will meet each level set at most once. And these single points where the toric strata is meeting the reduced spaces, these are the points where the reduced space is, these are sort of isolated points where the reduced space is not smooth. We can think of them as freckles on the reduced space. So again, everything here is complexity 1 now. So the reduced spaces are going to be either two-dimensional or single points. And let's spell this out. So complexity 1 means the torus is 1 less than half the dimension of the manifold. So I just spelled out the dimensions in my notation. And here's the momentum map and the momentum image. And here is the orbital momentum map on the level of the quotient. Now the dimension of the quotient is n-1. I'm sorry, the dimension of the target is n-1. That if you sort of wrap your brain around this, the dimension of the quotient is going to be n+1. So the level sets are going to be two-dimensional, except some of them might be single points. So in fact, the momentum polytope can be decomposed as a disjoint union of what we call the tall pieces and what we call the short pieces. By definition, the tall guys are the points in the momentum image where the reduced space is a two-dimensional. It will be, topologically, it will be an oriented surface. And the short guys are when the reduced spaces are single points. And what we call freckles, the points where the reduced space is not smooth, are the intersection of the two-dimensional reduced space with toric strata. And maybe just a little comment here, the short guy is just a union of faces of delta. So let me draw the picture. Here's the picture. This guy is, let me sort of restrict my attention to the part of the manifold, the tall part of the manifold, the one where all the reduced spaces are two-dimensional. I'm just ripping out those faces of the momentum polytope whose preimages where the reduced spaces were single points. So here's the orbital momentum map. Here's a point. The level set of that point in MRT is just some surface. And where do the freckles come from? The non-smooth points in the surface. We might have this X mod T, this toric stratum in the manifold that meets my level set in the quotient in exactly 1 point. And that toric stratum is in MRT. This is just a polytope. The orbital momentum map identifies it with a polytope in T star. And these toric strata, they can fit together. You can have one toric strata and then another, and they're going to fit together. They're going to be glued. They're going to be polytopes glued along common faces. So in mod T, or let me, mod T, toric strata are convex polytopes in the compact case. Otherwise, there will be convex polyhedral sets glued along faces. And phi, the orbital momentum map, identify each of them with an actual geometric convex polytope inside T star. And if you remove the toric strata, if you take minus the, so actually let me do M mod T, let me do tau mod T, minus, once you remove the toric strata, you get something which is smooth, oriented, everything is nice and beautiful. Now, it turns out that a very, very important part of the, of the story here is how do the toric strata sit inside the ambient M mod T? And it turns out that they can be embedded in some very interesting ways inside M mod T. This doesn't, and how are they embedded in M mod T? We call this a painting because we think of this as sort of painting sort of little sheets, horizontal sheets inside M mod T. If there exists an invariant Kähler structure, the painting will be trivial, but otherwise you can have some very interesting paintings. So I have to tell you a little bit about that. I will pause for another minute to see if there's more questions. Let me talk about trivialization of the quotient. Let me take just the part of the manifold where the reduced spaces were two-dimensional, that's M tau, mod T. So we've got the orbital momentum map. It turns out that topologically speaking, this guy is homeomorphic to just a trivial bundle, to just M tau cross a polytope. I'm sorry, cross a surface, cross a tridimensional surface, which such that the momentum, that the orbital momentum map is just a projection. Now, there's no way of making this smooth because the smooth structure is kind of whatever. These guys come with freckles and the freckles keep changing from point to point. You can't make this smooth, but this is topologically, this is trivial. And then, so what is the toric skeleton? Is what you get from the toric orbitype strata. So by definition, this will be the union of the toric strata inside M tau. So I'm sort of ignoring the short piece. And I'm working in the quotient space. So this is sitting inside the quotient, which I can trivialize. So composing everything here, how do the toric strata sit in the quotient? This is encoded in a map from the toric skeleton to the toric skeleton itself can be just thought of as a bunch of polytopes glued along common faces. This is it. But topologically, it can be interesting. And you have a map from it to delta tau. This is the orbital momentum map, but there's another component, a map from it to the surface, depends on the trivialization. And this is what we call the painting. And now I can state the classification theorem, or a big part of the classification theorem. And before I state it, let me make a little sort of, again, reservation here. This theorem, in the case that there's no short pieces, this is published in a sequence of 3 papers, where the last one was appeared in 2014. And the case of general delta, I'm telling you what we expect, but this is not yet, this is still in progress. So the details we're still writing up. So we're going very, very slowly here. So what does this classification theorem, or a piece of the classification theorem tells us the following. So take a complexity 1 Hamiltonian intersection with the usual assumptions. So M is connected. The momentum map is proper. You can get away with less than that. You can assume that the momentum map is proper as a map to some convex subset of T star. This is actually a useful assumption when you want to break the manifold into little pieces, pre-images of little open neighborhoods. So these guys are classified by the following pieces of information. And I reached the end of my page. I will now flip to the next page to get the list of invariants. First of all, the momentum image. In the toric case, that's enough. That's it. Second, the Drustumat-Heckman measure. But as I said, this is mostly determined by the other guys. Third, the genus. Fourth, genus means genus of the reduced space. They're all going to have this, they're all going to be surfaces of the same genus. Fourth, the toric skeleton. So the toric skeleton, again, is the image of the toric strata inside the quotient. But we think of it as actually equipped with the orbital momentum map, which is restricted to each piece. It's just an embedding as a polytoken T star. And we actually equipped it with some information called isotropy labeling. We actually remember what the isotropy representations were on the pieces of H. We have the painting that I mentioned, which tell us how the toric skeleton is sitting inside the product. The painting as is depends on the choice of trivialization of the product. But we know exactly what the ambiguity is. So this is up to the following thing. If you have two manifolds and two and their corresponding paintings, here's one of them. Let's just focus on the F part. So two paintings are equivalent if they differ by an isomorphism of the skeleton and a homeomorphism of the fiber of the surface and homotopy through paintings. And if you allow those changes, then in fact, up to this guy, the painting is actually unique. If you, up to this guy, the painting is determined. You don't need, it's independent of the trivialization. And this is the end of the statement of the theorem. Let me say a few words and then maybe give, in the last half minute to give an example. So when you do classification, you need a few things. You need to give well-defined invariants. So for example, the fact that we need the painting to be up to certain things, you need it for it to be well-defined. You need to say that these are complete invariants. This is the uniqueness part of the classification. It means that if two Hamiltonian, complexity one Hamiltonian torus sections have the same invariants, then they are isomorphic. And then the existent part is a piece that I did not write down. The existent part tells you that if you have a collection of invariants that are compatible in a certain sense, you can actually build a manifold that gives these invariants. And this existent part actually has a very, very nice corollary, which is, that allows you to do surgery. So if you start with any complexity one Hamiltonian torus section, let me focus on tall guys, you can always construct other ones that have the same momentum image, the same Drustumat-Heckman measure, the same skeleton, but where the reduced space can be of any genus. This here it's important that we work in the tall case, and the painting can be any painting. So you can start with something nice, something that maybe you obtained from a symplectic toric manifold by forgetting a piece of the action, and that then the genus is 0 and the painting is trivial. But this surgery allows you to then get other genuses and other non-trivial paintings. And maybe I'll get, maybe 2 more words in this last half minute. If the manifold admits an invariant Kähler structure, then the painting is in fact trivial. If not, that the painting could be quite interesting. And here's an example of an interesting painting that this is sort of the phenomenon sort of discovered by Sue Tolman. You could start with a symplectic toric manifold whose, and then forget a piece of, forget a piece of the torus section. This was two torus and a 6 manifold, where the images of the orbital type strata look like the black and red things. Think about this as sort of kind of a house with a roof, where you truncated the roof, and then you also have walls of the house. So everything is tall. Like the reduced, we're looking from the top, the reduced spaces over the boundary are actually 2-dimensional. So this is a tall case. And then if you extract the skeleton, it has a sort of a pi1. It has an interesting pi1, and you can actually arrange the painting. You can actually arrange a space of that type, where now you perform surgery, where the reduced space becomes of some higher genus, and you can actually arrange the painting to be non-trivial topologically, to sort of wrap around a non-trivial loop inside the reduced space. So that's kind of an example of an interesting painting, which cannot occur in the equivalent indicator case. And I will stop here, and and that's it.
Thank you very much.